Hello children, greetings. So we have already seen in the ray optics the reflection part of the topic. Hope you would have understand the sign convention of the reflection part from the mirror. Now, as a sample, we are going to see here, suppose the lower half of the concave mirror. You see here lower half of the concave mirror. So this lower half of the concave mirror is covered with an opaque reflecting material, non-reflective material. So it's going to be covered with non-reflecting material. Let us suppose. So I'll take a shape and then I'm going to cover the same thing. So the lower part alone, let me cover it. So this completely covered the lower part, only upper part is for the reflection. What effect will this have an image of an object placed in front of the mirror? Will you be getting the image or not getting the image? Even though the lower part is covered, our argument is whether you will get an image or not. First part. Now, the upper part is undergoing reflection. You must have noticed that. So, the upper part is undergoing reflection. Since the upper part of light is undergoing reflection, the beam of light rays which is coming from the object. So, the beam of light rays which is coming from the object undergo reflection and then it produces an image. But though it is producing an image, the intensity of the image, aperture, reduces, therefore the intensity is directly proportional to aperture square. So since it is directly proportional to aperture square, so what happens? The intensity get reduces. So can we check the answer? Yes, we can check the answer here. So what is the answer here? It is given. You may think that the image will now show only half of the object. But taking the law of reflection to be true for all points of the remaining part of the mirror, the image will be that of the whole object. However, as the area of the reflecting surface has been reduced, the area is reduced, I mean the aperture is reduced, the intensity of the image will be low in this case. So, you get an image, but only thing the intensity is reduced. So, same way 9.2, I am not taking the height of the image like that, size. Instead, horizontal size I am going to take into consideration. So, this is a finite distance. Since it is a finite distance, the different parts of the mobile phone will undergo reflection and produce an image at different distances. So, you will get beyond f, between f and 2f. So, between f and 2f, the object is going to be the beyond 2f, the image is. So, enlarged image. So, you must have noticed that which part of the image is going to be the enlarged here and then difference in the size. So, the ray diagram for the formation of the image of the phone is shown. The image of the part which is on the plane perpendicular to the principal axis will be on the same plane. It will be of the same size. You can yourself realize why the image is distorted. Size is same, but it is being distorted, but because each and every point of the mobile phone is undergoing reflection. It is it's not the size is no horizontal. I'm not taking the vertical one. So you have to take the consideration of the size, the distance into account. So you get a distorted image. Okay. Now come back to this. So let us see one problem based on the concave mirror. First, an object is placed at 10 centimeter. First question we will discuss. First question we will discuss in front of a concave mirror of radius of curvature 15 centimeter. So this is radius of curvature 15 centimeter. But it is placed at what centimeter? It is at 10 centimeter. So here 10 centimeter the object is placed. Now radius of curvature is 15 centimeter. Therefore we know that r is equal to 2f. Therefore f will be equal to r by 2, which is equal to 15 by 2 centimeter. Find the position, nature and magnification of the image. First of all, write down concave mirror formula. Can you try? 1 by f is equal to 1 by v plus 1 by u. You have to apply sign convention. So this is the light comes from the object. Since the light is coming from the object and you have to measure the distance from the pole of the mirror. So u is equal to negative. So minus 10 centimeter. R is also negative. So minus 15 centimeter. So therefore f is equal to minus 15 by 2 centimeter. So therefore 1 by minus 15 by 2 is equal to 1 by v plus 1 by u. So u is minus 10. So therefore I am taking it like that. So therefore I am taking this as minus 2 by 15 is plus 1 by 10 equal to 1 by v. Now take LCM. So when you take LCM, 30 is LCM. So therefore it is 30. So 2 to the 4 plus 3 is equal to 1 by v. So therefore what is v is equal to? What is v is equal to? Minus 30 centimeter. So we found out the answer. Find the position, nature and magnification of the image. So image position we found out. Nature, v is negative, u is also negative. So nature is real inverted. So real and inverted. Okay, right? We'll have to find out the magnification. Magnification of the image. M is equal to plus v by u. So here how to find out the magnification of the image. We have already learnt the magnification of the image. M is equal to minus v by u. That is for the mirror. So same thing I have to put it here. So m is equal to minus v by u. So I put here m is equal to minus v by u. Okay. So m is equal to minus v by u. So m is equal to minus of minus 30 divided by minus 10. So therefore that is equal to minus 3. So what do you mean by that minus 3? Minus 3 represents that image is magnified. So though the image is magnified and it is inverted image, that's why negative sign. Inverted image. So you found out the position, that is v is equal to minus 30, nature, magnification, all that we found out. So hope you understand this, and we will go to the refraction now. Refraction. What is refraction? Reflection over, now refraction. Now regarding this refraction is concerned, I would like to show one simulation. So we will see that simulation. Yeah. So you can see here. Now this is the ray of light. It is from denser, rarer medium to denser medium. Air medium to water medium will take. You can see here this index of refraction is 1.33. So therefore denser medium has higher refractive index than that of the air medium. So now we'll check on that. Okay. So we'll check on that. Speed will check in the rarer medium. Yeah, 1c. What is 1c? 1c is nothing but 3 into 10 power 8 meter per second. So that is 1c. Now, what happened to the speed of the light in the denser medium? You can check here this denser medium speed. Yeah, it is 0.67 c. Have you noticed that? It is 0.67 c. That is reduced. Earlier it is 1 c. But here in the denser medium it 0.67 c. So refractive index is glass medium. So since the refractive index is glass, so therefore the glass refractive index is higher than that of air, so hence speed reduces. Now what happened to the intensity? Check 100%. So the intensity also reduces because some of the rays have been reflected. So hence intensity reduces. Okay, just come back. Now the rays of light is bending. So therefore the speed also reduces. So what is refraction? The bending of light rays, when it travels from one medium to another, you call it as refraction. So the bending of light rays. Bending of light rays. when it travel from when it travels from optically rarer medium, optically rarer medium, optically rarer or denser, whatever. Bending of light rays when it travel from one medium to another medium. So that means optically rarer medium to denser medium, or optically denser medium to a rarer medium, whatever. So bending of light rays from one medium to another medium, one medium to another medium. Is called refraction of light. So when the ray of light travel from rarer to denser medium, rarer medium to denser medium, when it travels from rarer to denser medium, bend towards the normal. So it is bending towards the normal. Why does it bend towards the normal? Because the speed decreases. Speed decreases. Whereas the rays of light is traveling from denser medium to rarer medium. So this is the denser medium. So the ray of light is traveling from denser to rarer medium. Denser to rarer medium, bend away from the normal. So whether it is rarer to denser or denser to rarer, since it is bending, why does it bend? Because of the refractive index, because it is getting slowed down. So this is called as, this phenomena is called as refraction. So you can just check the book. What is the law of refraction? So you can check the book and then find out what are the laws of refraction. So in the meantime, I'll just come back. So, hope you found out the law of refraction. So, and then can we recapitulate the same thing for the law of refraction? Yes. So, what are the laws of refraction? Is it the first point, is it the same as that of law of reflection? Yes. Number one, the incident ray. Incident ray. The refracted ray. Where does the ray of light refracts? In the second medium. So, the refracted ray and the normal to the point of incidence. Normal to the point of incidence. Point of incidence. All lie in the same plane. All lie in the same plane. See, perfectly all the light will not be undergoing refraction. That is what we have seen. Some of the light will get reflected or transferred back to the same medium. So, we have seen the same thing here. So, that is what, there is a reduction in the intensity. Here 100%, but here only 90.81%. What about the remaining? It would have been reflected back to the same medium. So, the same concept here. The same concept here. So, now the incident ray, the refracted ray and normal to the point of incidence all lie in the same plane. Number 2, the law is nothing but Snell's law of refraction. What is the Snell's law of refraction? States that the ratio of the sine of angle of incidence in one medium to the sine of angle of refraction in the other medium, I mean the interface, that will be equal to a constant. That constant you call it as mu, or you can also write it as n. So, mu, which is equal to c by v, where c is the speed of the light in air, or you can write it as v1 by v2, or you can write it as nu into lambda 1 divided by nu into lambda 2. Already we know that we have discussed that the frequency of the light when it travels from one medium to another medium. So, this is denser medium, this is rarer medium. The frequency of the light source emit with a certain frequency nu. But when it comes over here, all the molecules set into same frequency of the oscillation of the source. They set into forced oscillation. Since it is setting into forced oscillation, they attain the same frequency, of source. So, therefore, the frequency of the light when it travels from one medium to another medium does not even change. So, therefore, I can write it as sin I by sin R is equal to mu, which is equal to V1 by V2. So, this is Snell's law of refraction. So, we learnt the law of refraction. So, this is the diagram for the same thing, refraction of light. You must have noticed that in this refraction of light, this is the incident ray of light, and part of the light rays is getting reflected, and then the whole part, 90% of the part is getting refracted, as because here this is the denser medium over here. So, the angle of refraction is R, angle of incidence is I. So, this is the refraction of light, and now we know the law of refraction of light. Only thing you have to know about the rectangular glass slab, how is that refraction takes place. Just the basic outsketch of rectangular glass slab you learn, because last year what happened, they asked this rectangular glass slab, the sides are going to be parallel to each other. The refracting sides are parallel to each other. What will happen? There won't be any angular deviation. You check here, this is air medium. So, this is glass medium. The ray of light bend from air to glass, bend towards the normal. Again what happens? Here the glass to rarer medium, bend away from the normal. So, this is angle I, so therefore, this is angle E. Since the surfaces are going to be equal and parallel, mainly it is parallel. So, what happens here? Angle I is equal to angle E. So, therefore, no angular deviation, Okay, there is no angular deviation. Will there be any lateral displacement? Yes. So, there will be a lateral displacement. So, this is called lateral displacement. There will be only lateral displacement of the wave, I mean the ray of light. So, lateral displacement is d, which is nothing but the perpendicular distance between incident ray, extended incident ray and emergent ray of light. Extended incident ray and emergent ray of light. Emergent ray of light. So you have to extend this incident ray at the back, and then here this is emergent ray of light. That distance you call it as perpendicular distance, you call it as lateral displacement. You can also derive the lateral displacement equation, so but that's not required. So if you want, you can just learn only the formula. So that is lateral displacement D is equal to T by cos r into sine of I minus r. T by cos r into sine of I minus r. This is lateral displacement. Okay, where T is nothing but the thickness of the glass slab. Now, when does the lateral displacement is going to be minimum? So note it. Okay, for a normal incidence, exactly falling normally, that is angle of incidence is 0. For normal incidence, or you can say angle I is equal to 0, then the lateral displacement is said to be minimum. I mean, there is no lateral displacement. Lateral displacement is minimum. So this was a question which was asked in the last year, hence I am discussing the same thing. So we know the refraction of light, then we will go for the relation between real depth and apparent depth. Relation between real and apparent depth. Real and apparent depth. Now I am going to take a denser medium. So let me take a denser medium here. So I am taking a denser medium. Now this is a normal ray of light. This is a normal ray of light. Not ray of light, I am sorry, this is a normal which I am drawing. I have drawn this normal. Let it be. I am going to place a coin at the bottom of this glass slab or bottom of the tank. So I am going to place a coin. So we will place a coin here. Okay, so let me just place a coin here. I place a coin here. The coin can be viewed in two different ways. This is a coin that is called as object. The object is going to be viewed in two different ways. So one, I am going to view it normally. This is called normal view. Perpendicularly I am going to view. When you view, always the light comes from the object. So the light is coming from the object. So exactly the light comes from the object and then reaches the observer's eye. No deviation, nothing. Just like that reaches observer's eye. So wherever the coin is, it appears as if the coin is in the same position O. So therefore, you call it as AO is called as real depth. So let me rub off all this. Okay. So now AO is called as real depth. This is medium. What medium? Denser medium. Please listen carefully. This is denser medium. What medium this is? Rarer medium. Refractive index is mu. So now I am going to take OA is equal to real depth. Real depth of the object. Really the object is at point O. So this much depth is the real depth. Okay. Now I am going to view the coin obliquely like this. Obliquely I am going to view the coin. When it is obliquely, the ray of light have to travel from denser medium to the rarer medium U1. So when the ray of light travel from denser to the rarer medium, the ray of light bend away from the normal. So it is bending away from the normal, reaches the observer's eye, produce the rays of light at the back. When you produce the rays of the light on the back, the image, that means the object appears, I mean the image obtained, will be at point I as if it is at point I. But actually where was the object? The object is at O. But here the object appears as if it has been raised at point I. Have you ever noticed in the normal life, you put Like, you take a beaker full of water. Yeah, glass beaker full of water. Not the smaller one. Take one bigger one. You should have some depth. It's not like very, very smaller. So, I mean, if you take this bottle, larger than the size of the bottle you take, as well as wider than the bottle size you take, and put a coin inside. When you put a coin inside, and by the side, if you're going to view the coin like that, you must have definitely noticed the coin would have slightly raised. Also, apparently, the shape of the coin also would have been little different. How come the coin is slightly reduced, slightly raised? It is only due to the refraction. Spoon. You put the spoon inside, and by the side you view, it appears as if it is bent. Similarly, take pencil, put it inside the water that's present in a trough of water. Trough. So, glass trough. Put that pencil and then you look by the sideways. You must have noticed that the pencil appears as if it is bent. Same way here also, the image is appeared, raised. So, OA is real depth. AI is apparent depth. Apparent depth. Okay, got it. Now, here the object appears as if it is at point I. Now, this is R, so therefore, this is also R. You must have noticed there are two set of triangles. I am going to take, now what is the assumption here? You must have noticed the assumption, angles are small. That is the one and only assumption. Angles are small. 1 degree, 2 degree, 3 degree, like that. Now take triangle OAB. Can you identify the triangle OAB, children? Yes. So this is OAB. Yes. In this triangle OAB, can you say that what is sin I? In this triangle, sin I is equal to AB divided by OB. Equation number 1. Hope you got it. Triangle AIB you take. So I am going to take AIB. So take the triangle AIB. So when you take the triangle AIB, you will get what is sin R. Sin R is equal to AB by BI. This is equation 2. Now, where is the ray of light coming? Is it coming from rarer medium or denser medium? No, it is coming from denser to rarer medium. Denser to going to rarer medium. So, mu 2 to mu 1. So, I wanted to write down the Snell's law. So, therefore, mu 2 to 1 is equal to, what is mu 2 to 1? That's 1 by mu. Okay? Mu 2 to 1 is equal to sine of angle of incidence divided by sine of angle of refraction. Or 1 by mu is equal to sin I, that is AB by OB divided by AB by BI. How do you know? Because we have taken this here, sin A is AB by OB. Is that clear? Similarly, what is sin R we have taken? AB by BI. Is that clear? Same thing I substituted. Is that very clear, very easy? Now, you know very well that AB get cancelled. So, therefore, 1 by mu is equal to BI by OB. Okay? So, BI by BO. Therefore, mu is equal to OB divided by IB. But, since angles are small, so therefore, point B lies closer to A. Point B lies closer to A. So, therefore, I can write point B lies closer to A. So, therefore, I can simply write mu is equal to OB by IB can be written as, approximately you can write it as OA divided by IA. Children, what is OA here? You have written here what is OA. You have written no. What is OA you wrote? OA is real depth. A is what depth? Apparent depth. Write down the same thing here. So, therefore, mu is equal to real depth by apparent depth. That's all. Real depth divided by apparent depth. style I am going to write this as mu is equal to RD by AD, real depth by apparent depth. That is all. So, real depth I am writing as RD, apparent depth. Apparent shift. So, apparent shift, how much is the shift has happened? That is equal to real depth minus apparent depth. So, that will be equal to real depth, take it out, 1 minus apparent depth by real depth. So, that is equal to x is equal to real depth into 1 minus, what is apparent depth by real depth? What's that? Mu is real depth by apparent depth. What is apparent depth by real depth? 1 by mu, that's all. So, this is apparent shift. So, relation we got to know, real depth by apparent depth is mu. Apparent shift also we got to know. So, that is all this derivation. So, hope it is simple and you can learn the same thing. So, can we go to the next topic, the relation between real and apparent depth we have done. So, we will go to the next topic. What is the next topic? That's nothing but total internal reflection. Total internal reflection. So, that is otherwise called as TIR. Now, for getting into this total internal reflection, I am going to ask you certain questions or the phenomena which is happening in the day-to-day life. Have you ever seen glittering of diamond? Yes, you must have seen. Diamond, how does it glitter? At all angles it glitters. You take a diamond and then you rotate like that. When you rotate, you must have noticed that at all angles it sparkles out. So, diamond glitters. That is only due to TIR. In everyday's life, every day nowadays we are using internet cables. Have you ever noticed or have you ever seen a white color cable wire which is fastened outside to our house? So, that white color cable wire is an internet cable that is not actually a plastic wire, it is actually a glass fiber. So, this is based on the principle of total internal reflection. You must also notice that in all shops or multi-story buildings, or must have seen that showrooms, some LED lights must be kept inside the plastic fiber and it glows as if it is continuously glowing, but actually it is not a plastic fiber, it is a glass fiber. You must have also noticed that there is a flower vase. At the tip, you must have noticed only some glowing stuff in the tip of this wire, but actually it is not a wire, it is a glass fiber. That is also based on TIR. So, this cables, internet cables, how does the light is turning into TIR? Why do we use light? Because we want only electricity. Actually, from one end to the other end, for example, this is my PC, this is your PC. From one end to the other end, the signals have to reach from the station or from the dish antenna or from the point. So, now from the point, wherever from the point, so now here it will be passed through this optical fiber cable as in the form of light. After entering into this board, that is personal computer, nearer to that, this electrical signals, it will be converted into electrical signal. Light signals will be converted to electrical signals. So, the light signal will be transmitted to longer distance, and once after reaching the PC or to your house, this light will be converted into electrical signal. That is what is happening. So, of course, that later on we will see about transducer, conversion of light signal to electrical signal or vice versa. Now, coming to the point, the total internal reflection, the phenomena is applicable even in the cables. So, based on TIR it works. So, based on TIR, the sparkling of diamond, based on TIR, there are many other phenomena like mirage. is happening based on total internal reflection. So let us see what is total internal reflection. What is that TAR condition? All that we will see now in this topic. Before saying, I wanted to show you this. You must have noticed that the ray of light is rarer medium to denser medium. For all angles, you must have noticed that there is no possibility for the refracted ray to toggle back, refracted ray to come back. But I am going to take this medium as water medium. You can check that. And here I am going to take this as air medium. Now the ray of light is traveling from denser to rarer medium. Slowly you see, look at the angle of incidence. See, this is the angle of incidence. Now slowly what happens? I am increasing the angle of incidence, you must have noticed. Notice it here. Konja I am increasing the angle of incidence. When I increase, what happened? Yeah, wow, at one angle of incidence, that's called some 58 degree or whatever, the rays of light, instead of undergoing refraction, it come back to the same medium. That is called as total internal reflection. Of course, you must have now figured out for TAR not happening if you take rarer medium to the denser medium. For all angles, I am just noticing it. Is there any possibility for TAR to occur? No. So TAR is not happening from rarer to denser. Instead, if you are going to take it from denser to that of rarer medium, denser to the rarer medium, so the TAR is happening here. You must have noticed that. See, 30 degree no TAR, only refraction. And 45 degree also no TAR, refraction. Slowly I am just bringing to 50 degree. Slowly I am bringing to 51, 52 like that. What happens now? Check. Yes. So approximately then 50 degree or 52 degree TAR takes place, total internal reflection. Of course, the ray of light should travel from denser to rarer medium at one particular angle of incidence. The ray of light, instead of undergoing refraction, it come back to the same medium. That is called as total internal reflection. So let us see the total internal reflection here. Yes. So total internal reflection I am going to see now. Yeah. When a ray of light is traveling from, first of all, write down total internal reflection. When a ray of light travels from, when a ray of light travel from denser medium to rarer medium, denser to rarer medium, at one particular angle of incidence, at one particular angle of incidence, in the denser medium, the ray of light, or particular angle of incidence in the denser medium, the ray of light grazes the interface without undergoing refraction. This phenomena is called as, this angle, more than that, by increasing the angle of incidence, by slightly increasing the angle of incidence, slightly increasing the angle of incidence, slightly increasing the angle of incidence. Now by slightly increasing the angle of incidence, the ray of light undergo TAR, total internal reflection, to the same medium. Where is it? Just now I showed you, right? The same thing. So now this is the denser medium. Now this is normal. The ray of light, one particular angle of incidence, the ray of light just grazes the interface. It is grazing the interface. So at that point r is equal to 90 degree. More than that, if you are going to increase, slightly increase more than that. So what happened? Instead of undergoing refraction in the other medium, it totally internally reflected. So ray of light travel from denser to rarer medium. That is important keyword. At one particular angle of incidence in the denser medium, the ray of light grazes the interface without undergoing refraction. See, grazes the interface without undergoing refraction. Now by slightly increasing the angle of incidence, greater than the critical angle, the ray of light undergo TIR to the same medium, total internal reflection to the same medium. So hope you understand. Let us see the conditions for TIR. Conditions for TIR to occur. Point number one, the angle of incidence should be greater than critical angle. Point number two, the ray of light must passes from. Ray of light should travel from what? What medium to what medium? Completely denser medium to the rarer medium. Denser to rarer medium. Then only TIR will happen. You got it? So now we are going to find out a formula, relation between TIR, relation between refractive index and critical angle. Refractive index of the medium and critical angle. You must understand what is critical angle C. We will see that and then we will go for it. What is critical angle? Critical angle is nothing but, critical means neither undergo reflection, nor undergo refraction. Neither undergo reflection nor undergo refraction. So critical angle, it is the angle of incidence. It is the angle of incidence. It is the angle of incidence in what medium? In denser medium. Denser medium. For which? The angle of refraction in the rarer medium. The angle of refraction in rarer medium. That means denser air interface. The angle of refraction rarer medium is equal to 90 degree. That is called critical angle. So now we have to see the expression for the same thing. So I am going to take this mu2 over here, and this ray of light is traveling from mu2 to mu1. So now exactly when it is traveling, what happens? It is grazing the interface by making an angle r is equal to 90 degree. So therefore this is called as critical angle. Mu2, this is mu1. The ray of light is traveling from mu2 to mu1. So therefore mu2 to 1 is equal to. Mu2 to 1 is equal to sine I divided by sine r. But mu2 to 1 is there, no children. What is mu2 to 1? In class 10 you have learnt. So that's nothing but, always keep it in mind right now. Okay, at least now you learn. Mu 1 to 2, that is rarer to denser medium. Rarer to denser means simply called as mu. You take mu 1 to 2 simply called as mu, which should be written as mu 2 divided by mu 1. Always mu means mu 2 by mu 1. But if it is going to be mu 2 to 1, means the reciprocal, that's it, 1 by mu. So mu 2 to 1, or I have to write 1 by mu, which is equal to sine C divided by sine 90 degree. Why? Because if I is equal to C, then R will be equal to 90 degree. So R, I can write it as mu is equal to 1 by sine C. Does critical angle depends upon the color of the light? Yes. So you can write critical angle depends on color of light. Okay, right, which color has greater critical angle? Mu red is lesser than mu violet. Therefore, sin C for red is greater than sin C for violet. So which color has got greater critical angle? Red color has got greater critical angle because it has lesser refractive index. All these are TIR. TIR formula we know, TIR conditions we know, application of TIR. Application of TIR. I'm going to teach you poro prism and then later on optical fiber you can learn. So, number 1, poro prism. Poro means right angled isosceles prism. Right angled isosceles prism. Right angled isosceles prism. One angle is right angle. Two sides should be equal. That's called right angled isosceles prism. Made of glass. Made of glass of mu is equal to 1.5. So now I have to find out critical angle. Okay. So let me find out critical angle. Answer. So find critical angle. How do you find critical angle? Come on. Mu is equal to 1 by sine C, or sine C is equal to 1 by 1.5. So that will be equal to 0.6. So therefore C will be approximately equal to 42 degree. This is how we need to find out the critical angle. I know the critical angle. Now number 1 prism. I have taken one prism. This is 45 degree, this is 90 degree. Let me call it as PQR. Please listen carefully. This is actually an object. The ray of light from the object hits the surface PQ. How is it hitting? Check properly. Yes, normally it is hitting. Along the normal, if the ray of light hits along the normal, no deviation. How do we know? We have already seen that. Check. Along the normal, if it goes, no deviation. Yeah, along the normal it goes. Is there any deviation? No deviation. So same thing here. Along the normal it goes. No deviation. Just like that it is going to come and then hit. This angle is 45 degrees. So therefore this is also 45 degree by symmetry. Similarly here also 45 degree by symmetry. After this ray of light undergo TAR. How? Because angle I is equal to 45 degree, but angle C is equal to 42 degree. Angle I is greater than C. So therefore TAR takes place. So angle I is 45, angle C is 42, TAR takes place. After taking place, you get an image like that. That's the first diagram. Similarly, we'll go to the second diagram, number 2. 190 degree deflection. This is 90 degree. This is P, this is Q, this is R. Rays of light from PQ just hits the normal at 45 degree. Now this is also going to hit the normal 45 degree, just arrow mark. Now here also angle I is greater than angle C. So apdi just get reflected. Again it hits at 45 degree. Here also what happens here? Angle I is greater than angle C. So therefore image is 180 degree shift. The last one, trapezium. This is simple. This is 45 degree. This is also 45 degree given. The rays of light from the object hits. Now it is hitting at an angle, so therefore it bends, undergo refraction. After undergoing refraction here 45 degree, which is greater than the critical angle. Listen, that's all same. This is undergoing refraction, because it is not at an angle greater than the critical angle. So it is undergoing refraction. After undergoing refraction, exactly in the base while it is hitting, right, 45 degree it hits, greater than the critical angle. So therefore what happens? So this one undergo refraction, and then you will get only one time undergo TAR. You get 180 degree shift. So image is 180 degree shift. So these are the applications of TAR. Okay, applications of TAR. The last one, optical fiber cable application. Optical fiber cable. Optical fibers. Optical fiber cable you are using no for internet. How does it look? How is that? It has got outer cladding. That is made up of glass. You should say outer cladding. All these are made up of silica. I am going to show you inside textbook. The outer cladding, you call it as cladding, you are not able to read out. So let me use this. Outer cladding. It has been named as cladding. It is made up of glass, silica glass or quartz glass. then only what will happen, the life quartz glass and silica glass alone have the capacity to just have difference in medium. Glass, no, from the glass and TAR. Why do we choose that? Signal security will be there, speed, high Mbps, and no loss of signals, 100% security. So all signals will undergo TAR and then reaches the receiver end. That is why everybody is using this internet cable, ACT internet cable, you must have heard, not the landline cable. So it is like a plastic, white in color, milkish white. So, or wheatish white, I guess, some of the cables. So inside it is made up of glass only. Two different refractive index. Outer cladding, and then this is inner core. This is called inner core. Apparently, which one should have higher refractive index? Inner core refractive index should be mu2. Whereas outer cladding refractive index is mu1. So mu2 should be greater than mu1. Now what happens, the rays of light from air, it's directly into the inner core. After hitting, what will happen, it is hitting at an angle greater than the critical angle, so therefore TAR takes place, like that. So again TAR, so it goes like that. That's all. So optical fibers are made up of silica or quartz glass. Silica or quartz glass. It is made up of two materials, of course glass only. Inner core of higher refractive index. Outer cladding of slightly lesser refractive index. Light signals are passed in such a way that it has to first enter into the core, because core is a denser medium. Then it enters at an angle greater than the critical angle, so therefore what happens, TAR takes place. That is how we need to, that is how it works. So now you check on this. Okay, so now you check on this TAR. Yes, you must have noticed that the rays of light, it is undergoing refraction. You must have noticed that this also undergoing refraction. You must have noticed that this is undergoing grazing the interface. What angle it is grazing the interface? This is called as critical angle. Now more than the critical angle, if you are going to take this, or if you are going to increase this as more than the critical angle, instead of undergoing refraction, then it will undergo total internal reflection. See here, that is all. Total internal reflection. I was already talking about why does the diamond glitters. You must have noticed that the diamond refractive index is 2.42. So therefore, since the diamond refractive index is 2.42, this critical angle is very, very lesser as compared to the other one. So therefore, 24.41 is a critical angle which is lesser. So that means it will undergo TAR. Now come back here. We have seen all this phoroprism. Now look at this optical fiber. I have already pointed out the same thing only. You can draw that. In this optical fiber, outer core, inner cladding. Yeah, outer core, inner cladding. The same thing I have given in an enlarged form. So you can notice the same thing. Yeah, have you noticed that? Higher refractive index for the inner one and outer one is lesser refractive index. So TAR takes place and then you will have signals which is going in with 100% security, it gets reflected back. So you can learn the same thing here. You must have noticed that optical fiber can be used for transmission of optical signals. Have you seen that? It is optical fibers are used for the transmission of optical signals. Okay. The main requirement in fabricating optical fibers, there should be very little absorption of light as it travels from long distance inside them. This has been achieved by purification and special preparation of the material such as quartz. Is that given or what? So it is given us. So one more question will be asked. That's why I am making it to underline that. In silica glass fibers, it is possible to transmit more than 95% of the light over a fiber length of 1 kilometer. So all this, you can just make a note of it. So hence I am just spending time on it. So you can notice the same thing. So basically speaking, optical fibers based on the principle of TIR. Okay. So now even sparkling of diamond is also based on the principle of TIR. So hope you understand this TIR. Now the next we are going to go for refraction of a spherical surface and by the lens. So till then just learn till this topic. Thank you children.